In this video, I'm going to continue my coverage of derivatives. Now, if you'll remember from the equation of our last lesson, we had S5, which was a representation of the number of feet the ball had dropped for 5 solid seconds. Okay? And then we had a D here, which was the representation of the distance the ball had traveled since the 5th second. We're talking about instantaneous speed here, all right? And so after the 5th second, that ball is going to continue to drop until it actually hits the ground. Remember, you drop a ball from a roof, it's going to continue right on dropping until it actually hits the ground, all right? Now, you also have here the 16, and you have the 5, which is the number of seconds we were talking about, which is 5 seconds. And then you had this E here, which was the time that had elapsed after the 5th second. Remember, anytime that the time elapsed after the 5th second, the ball's going to drop a certain number of feet. Okay, that's just simple. All right. Now, why did we use the triangle over here? Well, the triangle, and I had already discussed this in a previous video, is called delta. Okay? And that triangle here is the Greek letter for delta, and it represents change. Okay? So, we're saying that there was an additional amount of time past the 5th second, which is a change in the time. We're changing the time, we're also changing the distance, because remember, we're adding more distance to the ball that has already dropped. Okay? And so, in the end, you have a ratio of the additional amount of distance dropped from the 5th second to the additional amount of the time that passed after the 5th second, equaling this. Okay, which is delta t right here. So what you would say is that the ratio of delta s to delta t equals this. Okay? Now, what is that 160? Well, that 160 is the number of feet that fall between the 5th second and the 6th second. It's an average of instantaneous speed. It's going to fall at least, the ball's going to fall at least 160 feet between the 5th second and the 6th second. Remember, the ball fell 16 feet in 1/10 of a second. So, and remember, because the velocity of the ball is going to increase, you're also going to have the distance that the ball is going to travel is also going to increase, because the greater the velocity, the more the ball is going to drop. Okay? So the ball is going to fall a minimum of 160 feet between second 5 and second 6. And we come up with this instantaneous speed because of this equation that we came up with. So 160 feet is the number of feet that the ball minimally is going to drop between the 5th and the 6th second. Now remember, we're also going to be starting to factor in gravity, which is going to make the velocity of the ball go faster. So it's going to drop more than 160 feet between that 5th and 6th second, but it's going to drop a minimum of 160 feet. Okay, so when we say 30 miles an hour, it's 30 miles divided by an hour. When we say 160 feet and it ends up being 0 because you're talking about instantaneous speed. You're talking less than a nanosecond. Okay, so this velocity is going to come up from less than a nanosecond. So you're saying that the average speed at the point between second 5, which is your ratio, your second 5, and whatever. I think you're kind of getting the idea here. We're talking about finding instantaneous velocity just as much as we had just found out about 30 miles an hour, which is an average velocity. Alright, if you have any questions, if you're still confused, leave me a comment down here and I'll try to go through this a little bit better. I know I'm kind of out here and it's getting ready to rain and I don't want to stay out here too much longer, so I will tell you more in a future video. Stay tuned.